and is from Washington State University. And he's actually the primary author of our Region's Guide to Low Impact Development. And he's working on, it's very close, the next edition on the Low Impact Guide, Guide to Low Impact Development. And our LID is the same as your SUDS. So just whenever you hear Low Impact Development, LID is the same as SUDS. So Curtis is going to acquaint you with what he's been doing at the Stormwater Centers and in their research trials, some of the results that he's been getting, and again, to bring our focus back to the stormwater performance values of green infrastructure.
Thanks, Nancy. Hello, everyone. I guess I've been brought in to help with your lunchtime digestion. However, I have a lot of data that may not be the right what's needed. But anyway, we are going to be looking at some data on low impact development research and facility that I'll acquaint you with as we move through the presentation. And thank you, Nancy, for a gorgeous lunch. I wish we had caterers. Wonderful. So we're going to spend, as Nancy mentioned, we're going to spend the lunch time here sort of getting into a different track and looking at performance, what we're learning about performance of some low impact development or green stormwater infrastructure or SUDS. SUDS facilities, and I'm going to try to relate that a little bit to some of my thoughts on this valuing question, because it's very interesting as far as understanding, of course, understanding performance, and then what are our costs and benefits to get the performance that we're hoping for out of these systems. And then I'm going to talk a little bit about. I'm just going to give you a very brief background on the research facility area, so you have some context. And then some of our data, some of our initial data, we're just getting started. And then also where we're going next and research that we're just starting on. And then I believe is that this particular research on integrating green stormwater infrastructure and aquatic toxicological research. The research we're doing here is the only research of its kind in the world, I believe, going on. And it's very interesting. So we'll talk a little bit about that. And questions as we go? Is it okay or hold it? Okay, if you have questions, please ask as we go. So I want to provide a little bit of background on the facility to give you a sense of what this looks like, the scale, the type of work we're doing. Fairly unique facility located about 30 miles south here, not too far, and it's being built into our oldest research center. So we're, UW is the state of Washington's Western research institution. Washington State University is located over in a lentil field, almost to Idaho. And I know for many of you don't know that, but the next state east of here, probably the most remote research, major research university in the United States. But we have research centers located around the state. This is one of them. This is the oldest one, and it was very much focused on agriculture. But the area has become much more urban, and so we've had to transition with that urbanization, change in demographic, and so we're really starting to focus more on much more on watershed science, and particularly stormwater management. But just to give you a sense of the lay of the land, we have bioretention, permeable pavement installations, rain gardens, and we'll talk more about the distinction here between these two. And we have also a greenhouse. I'll show you just a couple pictures of that, but columns where we have large columns where we can experiment with, at a smaller scale, experiment with materials and media with and without plants, for example, and different hydraulic regimes and that sort of thing in these systems. So we'll look at some pictures of these so you'll have a better sense. Some of the, a little bit of, again, background on this. About $1.5 million to build this facility. 1 million from the state of Washington, and about $500,000 from Washington State University in in-kind contribution. We're all done with construction, and we're constantly, I say your calibration is in progress. We're always calibrating, so I guess it's always in progress. And we're just getting, this is our first year of full experiments, and I'll explain more what that means by full experiment, running almost all of our systems now. And we're operating from grants from a number of entities from the state of Washington, U.S., United States Fish and Wildlife Service, local funders, as well as City of Seattle. I know there's at least one person from the City of Seattle, and I always thank you. A bit of wonderful support. Some of the things, again, just a little bit more background. There's going to be 2 slides on background, so not to worry. Spend much time on that. But a Center for Research for Green Stormwater Infrastructure and Education in Puget Sound, but also the West. We see this as a facility that really can serve Western United States as well as the nation as far as the kind of information that we're producing. What is really unique about this facility, and I know why no one else does this now, that is build full-scale facilities that are replicated. So that's very unique. There's very few places in the world where you see, either it's in a lab, in small scale, it's in a little column or something like that, or a little box and replicated, or it's full scale and maybe it's some monitoring out somewhere, one facility or 2 maybe. Well, we've built full scale facilities, but replicated, and I know why that's not done, and because it's ridiculously expensive and takes a lot of time. We've been building the facility now for, we've been at it for about 4 years now. This, again, is our first season we'll be in really near full operation. Another thing we're really working on is integrating this idea of integrating disciplines. And we see that, and I'm sure many of you understand this in the audience. We sort of stand at a new era as far as managing water there in the landscape. It's going to require integrating civil engineering, landscape architecture, soil science, plant science, aquatic toxicology. And so we're working with this facility to do that across many departments of WSU. And actually, with some success. A lot of, and of course, obviously this is one of our missions, right? Excellent graduate research, publishing opportunities. I also want to mention, because Nate is here from SVR, it's been quite a while. Nate in SVR, an engineering company here in Seattle, was the engineer on this facility. He worked with us and others, other engineers in WSU on designing and building this facility. And landscape architecture, that's right. All right, so a little bit about who works there. We have, again, this whole idea of trying to bring in different disciplines to bear on this issue of water management, the urban environment. Hydrologists, soil physicists, Jen McIntyre, glad to be Viking McIntyre, aquatic toxicologists, horticulturists, turf folks. So a whole sort of pretty broad spectrum of disciplines coming to bear at this project. So let's, again, by way of background, I just want to give you a few pictures of what's out there, and then we'll get into some of the initial findings from our research. And right now, again, I want to let you know that sort of where we stand. We've done a lot of initial baseline characterization of these systems. And that's another thing we see as very valuable information from this project is you've probably experienced this where you've seen research out there on performance of rain gardens or bioretention or permeable pavement, and it's not really clear where you started. What was the condition of the materials of that site before you started? What's the baseline starting point? We've spent a lot of time on that baseline condition, and that's what I'm going to talk about primarily. But anyway, we have, as part of this, we have these rain gardens that are installed in the ground. And again, they're full scale. This is something you might see installed in some jurisdiction somewhere along a roadway. or adjacent to a building. And, but there are 16 of these, and all of these systems have the same soil media, and it's a sandy compost medium. That's a medium that we use quite a bit around here. I'm not sure what other countries are focusing on, but here this material is a very particular kind of sand with a very tight specification and compost. And so these systems have all of that same material in them, but different plant palettes. So they're set up in a random block design where you have grasses, shrubs, and no plants. So here we're really focused on plants, very basic things. What kind of plant, plant health, establishment, those physical characteristics of those plants, but also looking at soil. How do these soils evolve over time? You direct stormwater to them and you have these particular kinds of plants in them. Physical characteristics, what's the permeability of that soil after 5 years? What are some chemical characteristics? And I'm going to talk more about this at the end as far as things that we're hoping to expand into and do more of.
What kind of soil do you have to use with compost?
Yeah, thank you for asking that question. It's great because I'd love to brag about this. The question is, what kind of soil do we have underneath? We have a soil type here that we call hideous, and it's we've analyzed. So this soil is very fine grained. It's alluvial deposits off channel. There's a major river system here just north of this facility, and this was part of that floodplain. It's a very fine grained soils. Very low permeability. Our operating infiltration rate for design was 0.003 of an inch per hour. So I'm sorry, I don't know what that is in milliliters, but centimeters. But many engineers would consider this impermeable, but quite low. And that's actually, it's actually not true. I mean, you can just do some arithmetic, and over a year's time, even 0.003 of an inch per hour, you can actually move some water into that soil. So, poor soils, very poor. All right, so I'll talk a little bit more about this at the end of things we want to do in the future. The other part of the bioretention research are these mesocosms. So that's just it's a word for an installation or a research plot that's sort of at a medium scale. And you see all these white tanks here. There's 21 of these. These systems have all the same plants in them, genetically the same plants, placed in the same spot, however, different medium, so different types of soil medium. So for example, we're looking at different ratios of compost to sand, and then we're working with different novel amendments to put in the media for particular characteristics. And I'll talk a little bit more about that in just a moment. So we're really focused on water quality, although we measure flow constantly. All the flows through these systems are measured all the time in 5-minute intervals, because this is actually a working stormwater system. Actually, should have mentioned that earlier. Another unique characteristic of this facility, this is actually a working stormwater facility. It's not just a research facility. And we came up with the crazy idea that, sure, we can build a working stormwater system and make it so that we can do research on it. And that was our initial goal, and it's working quite well. So different medium in these. There are 5 treatments replicated 4 times. And we'll look more at that list in just a moment. So the different soil mixes, we're really focused on all the usual constituents or contaminants in stormwater. Metals, hydrocarbons, bacteria, organics. But we're paying particular attention to phosphorus, nitrogen, and copper. And you'll see why in just a minute when we start talking about some of the data. These are the 3 contaminants or constituents that we believe that we're finding are the most difficult to deal with in these kinds of systems, in bioretention systems that have organic material. And you'll see in some of the data, we'll talk more about that as we go along. And then we're also interested in the hydraulic properties. And there's some things actually that we're still working on in our region as far as the hydrologic models that we use in this region. There's still missing pieces of information to improve the accuracy and the estimation provided by those models. And so we're looking at hydraulic soil properties that will, for example, help with refining our hydrologic models for these systems. But big focus on water quality. So here are the soil treatments. 60% sand, 40% compost. So that's by volume. So that comes out to something like, 5, 6, 8% or 5, 6% to 8% organic material by weight. If you were to look at these through a weight lens. 80% sand, 20% compost, 60% sand, 30% compost, 10% WTRs. Does anybody know what a WTR is? Other than those people that I know.
We have to know. We work for wastewater treatment plant. Wastewater treatment residual.
Yeah, actually, so the response was wastewater treatment residuals. Not quite. Not quite. These are actually water treatment residuals. So these are iron and aluminum hydroxides that are used in drinking water intakes to settle out the fine particulate material. So we're using these to hopefully bind up phosphorus in the system. So what we're working on a lot is, can we find waste products that we can put into these systems and improve the performance? That would be the ideal, right? I mean, you can go out and find new stuff. I mean, we could put activated charcoal and zeolite in these things, and they cost $1 billion to install. However, we're trying to focus on things that are waste products that might benefit these systems. So these WTRs are, particularly the aluminum hydroxides, are very good at binding up phosphorus, and that's one of the things we're finding can be exported out of these systems. So you can actually have more phosphorus coming out of the system than goes in. That's not good. That's a problem. 60% sand, 50% compost, 15% shredded bark. We'll see some data of why we're putting in shredded bark, and this is very finely shredded bark. The WTRs are fine-grained material. They're silky, clay-feeling stuff. And when you put that into a media like this, the permeability goes down. We put the shredded bark in it to bring the permeability back up. And the short message is, right now, is it works. We have some biosolids treatments in there right now. Taking those out, replacing the biosolids with some novel material that we're really interested in right now, and that's biochar. I'm not going to spend a lot of time on that because we can spend a whole hour just on biochar. The biosolids, we'll look at the data, some data. Since we have this concern about nitrogen and phosphorus, to me, putting biosolids in a bioretention system is just like, I would say, like prescribing pecan pie for a patient that has a heart condition. You're putting more nutrients into that system. You're shoving, biosolids are quite hot. They have lots of nutrients. So, and we'll see some of the data sort of verify. Okay, so just a little bit of background, so you have a little bit of context on what we think about in this region as far as bioretention and how we design them. So these are the main things we're trying to achieve in a bioretention system. High enough infiltration rates so that it meets the desired surface water drawdown and system dewatering. It needs to be permeable enough to, as water comes in, it then is drains through, moves through the system so it can be ready for the next storm. You don't want infiltration rates that are too high because you need contact time for those pollutants that you're trying to manage. The water needs to be in there long enough for that media to work on that water. And we need something that will support plants long term. The plants are critical. And I was in a meeting on maintenance the other day on these systems. And one of our jurisdictions, who I thought was actually quite advanced, we were talking and the guy says, do we really need plants in these? And I felt like, I thought we could settle that out. years ago. Evidently not, you know. And so what he was asking is, can we just have a sand filter? You know, let's just have sand filters. Well, there's, you know, anyway, plants are integral. They're absolutely critical to the systems. These are plant soil systems. So that's very important. Then there's, you see up here I have 3, and then cross that out, and it's really 4. Now I think as our research and other research that's going on right now, this is a 4th thing. We need to balance the nutrient availability and retention, nutrient availability and retention, and copper retention at very low effluent levels. So we're talking about, and you'll see in some of the data, we're talking about effluent at quite low levels, a few parts per billion of copper. What we understand in this region from research that's been done by by NOAA is that salmon, for example, are hypersensitive to copper. It degrades their ability to sense their environment, to smell their environment, to sense predators, to sense their natal stream, for example. So these are, you know, even very, very low levels of copper in the water can create a sublethal effect on the salmon that we're very concerned about in this region. And you can essentially, not outright kill them, but through those sublethal effects. So we're often, in this region, we're very concerned about, often, you know, constituents and contaminants at quite low levels. And it gets very difficult to manage. When you're talking about a few parts per billion, you're starting to get into a realm of very difficult, it's very difficult to reduce those levels any further. That's what we're working. Okay, little data. I'm going to start off, now these I should really have a little picture down here, but we're going to start off, we're going to spend a lot of time on the mesocosms. So those are the white tanks, right? The white tanks with the different media, same plants, right? So this is one of the things we did first. As I mentioned, we spent a lot of time characterizing our baseline condition. So we ran permeability tests, large-scale permeability tests in these, in the mesocosms. And I'm just going to go through sort of some big messages here. We don't have to dive too much into the minutiae of this. But one thing is, look at, this is kind of interesting. Here at 80-20, lots of sand, a little bit of compost, highly variable. Wow. And, you know, so this is when they're initially installed. And so probably not too surprising, because these systems are initially installed. It's probably not too unusual that you can see a lot of variability across that material. One lesson from this is, how restrictive are we going to be about testing new installations? In other words, this rain garden here that's infiltrating perhaps, you know, quite low, I'll show you data for the next year. How is that going to be performing in a year? It might be okay. Are we going to tear that thing out and put it back in, spend the money to do that, when perhaps it's not such a big problem? Just interesting as far as the variability that we're experiencing in these systems. And so how do we deal with that variability in our installation and maintenance? Interesting question. The biosolids, you know, is there any, you're with wastewater treatment. Any biosolids people here? Okay, okay, yeah, so, okay. I apologize to you up front. I am not a fan of biosolids. And these, what's that? Okay. I understand the good goal of what do we do with this stuff. I've pretty much fallen out on not stormwater filter systems. Oh, okay, yeah, sorry. So biosolids are a material, I mean, as much as I know about them, I mean, I know what they look like and pick them up at the wastewater treatment plant. But this is a product from, so this is sewage treatment plant material that's been processed, you know, dried, and processed, and perhaps mixed with other stuff. For example, a city just south of here, they mix in sand, sawdust, or other materials into their biosolids. And then market it. They sell it to people to put in their gardens. And it grows plants like crazy, because there is a lot of nitrogen and phosphorus in biosolids. So a wastewater treatment material, not a drinking water treatment material. So it's a sewage treatment plant material. And you can see here, as we expected, the biosolids mix was the permeability compared to the other systems quite low. And that's because the stuff's very fine grained. So the other systems you can see here, just again, we'll take some broad look at this. You know, this is and I apologize for us in America, we're still using English. And I do this because the engineers in this region, and I'm usually speaking to the engineers, like, could you put that in English units? You know, what's a centimeter per so, at any rate, I apologize, because it's silly. At any rate, quite high. You know, you can see here in inches per hour, you know, 20, 25, 30 inches per hour for these. Here's the 60% sand, 40% compost, and here's the mix where we incorporated in the LARC. So here is the system with the water treatment residuals, and here's the system with the water treatment residuals with the shredded bark added back in to improve that permeability. And in fact, that's what we're finding. That material works quite well for improving soil structure and permeability. So again, just kind of some big messages. So we're going to jump ahead now to the next year. Same graph, the next year. Okay, wow. A little more on the variability note. Here's the 80-20. Here's our first year of establishment, just installed. Here's the next year. Okay, brings, I think, to me, an important question of understanding that we need to understand the variability in these systems. They're plant soil systems. It's not a sand filter, that you have a very tight gradation and you can say, you know, with a high degree of confidence, it's going to be this permeability. These are plant soil systems, higher variability. How do we manage that in our installation and operation and maintenance? So another I think message out of this so far. A positive note for the biosolids, a little bit higher. The infiltration rates came up on that. What we see what we expect in these systems is they establish, and the plants establish in those systems, and the roots penetrate that soil column. Soil structure is improved, increased. You get the physical penetration of those roots that we may be seeing. In some cases, it looks like we are. Permeability that's actually increasing. So that'll of course be a very positive. Okay. Still on the mesocosms, on the white tanks. Here is some baseline soil analysis. So we're sampling our soil at various depths every year. Baseline numbers, and then see how that soil evolves over time. One of the big questions is, if you're directing stormwater to rain gardens, are they, you know, the question I get often is, are these going to become toxic waste dumps? You know, are you going to have to deal with this soil in some special way? So we're looking at these soils over time, both physical and chemical characteristics. So just a couple, again, sort of a broad brush look at this. Again, you know, right off the bat, on the biosolids, very hot as far as nitrate and phosphorus. Quite high compared to these others, particularly in the nitrogen. The other is there's a lot of phosphorus in these systems, and that's a management challenge. So this is the same information, just in graphics. So this is our first year baseline analysis for nutrients, and then here for metals and cation exchange capacity. So another important measure, of course, another important soil attribute and measurement. Again, on the biosolids, we're seeing the copper quite high compared to the other materials. Big management problem with biosolids, if this is representative, which we think. Other than that, you know, I think another thing, cation exchange capacity is an important measure for us as far as how well these systems behave as far as, for example, capturing metals. And all of these systems have quite high cation exchange capacity, so that's very good news. and I think something that will not be an issue or a challenge with these systems. So again, this is the first year baseline, and then we'll be sampling these every year to see how this changes over time. Really interesting, important information as we move through, as these soils evolve. Another issue we're having, or challenge, is how do we, when we specify a media for bioretention, what measure do we use? What metrics do we use to say that media is okay or it's not okay? And there's some things that are fairly straightforward. The phosphorus question is not straightforward. It's not easy. What measure do you use? We've used, tried several different measures of phosphorus in soil to understand how much phosphorus is locked up in that soil and that might be released. And we've looked to the agricultural world for that. For example, in this region, gray phosphorus is a metric that the agricultural people use. And we're finding that doesn't really work. It doesn't really tell us what the potential of phosphorus release is. What we are looking at now, and it's not clear whether this will work, is a thing called an oxalate extraction for phosphorus and iron and aluminum. So it's the ratio of a particular kind of extraction of phosphorus to an oxalate extraction of iron and aluminum. And the ratio of those potentially shows some promise of telling us this soil is okay, this media is okay to place, or it's not. And basically, that ratio is above 0.25. That is a level of concern that you might expect phosphorus released from these systems. Well, all of these were were fine except for the biosolids, but we're not yet seeing a solid correlation. So this is, again, it comes back to this: how do we specify? How do we better assure that we're getting quality product in the ground and that it will work? All right, so one of the other thing we did as far as characterizing our systems up front was we did a gigantic leaching test. I don't know if this has ever, I don't think this has ever been done anywhere, where we used those mesocosms and we ran tens of thousands of liters of clean, potable water through them to see, well, right off the bat, what would come out of these systems if the water was quite clean. If you had stormwater, for example, it was fairly clean. And again, we'll just take a broad brush look at this, but we'll look at phosphorus in particular and the nitrate. And so let's look at, to start with, let's look at the nitrogen. Well, this is our influent monitoring station. This tells us what's going into the system. What are the concentrations of contaminants coming into the tanks? And you can see here on the let's start with the phosphorus. Well, this is potable water, so it's quite low in phosphorus. See right here. And this is the effluent levels, and these numbers right here are the effluent levels, the water coming out of the tanks. Well, you can see here where it's right here on this mix right here, which performed the best actually. We were an order of magnitude more phosphorus than what went in. Still somewhat low level, but definitely a level of concern. And it just got worse from there. The 80% sand and compost and on down the line here. We're seeing export of phosphorus out of these systems. And we're not the only group that has observed this. We've also seen export of phosphorus out of other systems that just have soil. They're loamy soil in the system. The agricultural world, I think, lends some information to this in that we know from agriculture that when you disturb soil, when you till it, stuff comes off of that field. Nitrogen and phosphorus come off of that disturbed soil. Well, these are disturbed systems. We're taking a media that we've designed, mix it in a big bucket or whatever, throw it in a hole, and the whole thing's it's all mixed up and disturbed.
First, is there a time component to that? When does it come back down?
Right. Good question. The question is, how would these levels change over time? We don't know. And we're, you know, that's one thing we'll be watching is how does this change? And also, so let me get to the next slide, and that'll help explain. So let's see. We wanted to also look at nitrogen, nitrate. This was actually very promising. Our levels of nitrate in the systems performed pretty well. We didn't see a dramatic increase. That's good news. We've seen from other research, nitrate in particular, very elevated levels of nitrate coming off some of these systems. So again, this is all part of the initial characterization to then over time be able to say how will these systems evolve. All right, so question?
Oh, excuse me, can you go back one slide? What the flow, you are writing the flow and then you write liters? Is that the total amount of liters?
Correct, yes, yeah, thanks for asking that. Yeah, so the question is this last column here for flow, the total amount of flow in liters for each one of these? Correct.
And how long time have you?
What was the time frame?
Yeah.
Oh boy, it was less than 12 hours.
Okay.
I'm trying to remember exactly what the time frame was. If I remember correctly, we ran this. This is an artificial, of course. We ran it up to this fairly high flow level, and then kept it constant because we felt that was the worst case scenario, the most conservative test. And I think we ran that test for about 6 hours.
And you kept the constant?
We kept it fairly high. We ran up the flow quickly, and then kept it fairly high for most all of that period.
Okay.
Again, because we wanted to really test this system.
What's DOC?
Dissolved organic carbon. Okay, the question, yeah, what is DOC? Dissolved organic carbon. And thank you for asking that. This is a really important one. You can see the water was quite clean, and we saw